Hello. In this lab, this is our pre-lab for our water rocket lab. And in this lab, we're going to measure and calculate the static thrust of a pressurized water bottle rocket. Now, the thrust inside of the bottle rocket, is a function of time. So we're going to have to calculate what that thrust is. And we're going to find out that the thrust is equal to what's called the momentum flux, density times the exit velocity squared times the area. And we're going to derive this in just a little bit. The exit velocity depends on the pressure in the tank, but pressure is a function of time, so we have to calculate the pressure. And then the pressure depends on the volume of the air in the rocket, which is changing in time, and that depends on the height of the water. So we're going to have to calculate the height of the water as it's changing. So first I'm going to develop an expression for measuring the thrust in the lab, how we're actually going to measure the thrust. And then we're going to do a theoretical calculation. And then in your report, you're going to compare the theoretical calculation with the measured value of the thrust, and then try to develop a model which accurately predicts the static thrust. So to do this, we're going to start with a diagram here. Now, before you do this lab, you need to read the write-up. Before you do this pre-lab, read the write-up so you'll know what I'm talking about. But we have a water bottle, and inside this bottle, there's a portion that's occupied by pressurized air. Then there's water down here. There's an exit area, which the water escapes through here with some velocity. And I've labeled the dimensions here. We have the height of the total bottle, not including the nozzle here, is big H. The height of the water inside the bottle is little h, and then the height of what's remaining is big H minus little h. Now I'm going to do a free body diagram, and then we're going to sum the forces on it. In our free body diagram, we have a reaction force up here at the top. This is where it's held up. We have thrust at the bottom. And then inside the bottle, we have a body force. We have the weight of the water plus the weight of the bottle. WB stands for the weight of the bottle. And I've called the Y positive in the up direction. So if we sum the forces on this bottle, the sum of the forces in the Y direction are equal to the thrust minus the reaction force minus the body force, which is the weight of the water, minus the weight of the bottle. And because the bottle is held still, there's no acceleration, so it all equals 0. F equals ma. So we can solve that for the reaction force. The reaction force is equal to thrust minus the weight of the water minus the weight of the bottle. Call that equation 1. Now when we start this experiment, when we're measuring the thrust with the load cell, we zero out the load cell so there's no reading on it. So R prime is what we're going to call the reading on the load cell. And since we do zero it out at time equals 0, and at time equals 0 there's no thrust because we haven't started the experiment yet. So we can say that the reaction force at time 0 is equal to minus the weight of the rocket at time 0 minus the weight of the bottle. And therefore, the reading on the load cell is equal to the actual reaction minus R0, which is equal to R minus the weight of the water at time 0 minus the weight of the bottle. Solve this for R, and we get the reaction force is equal to the reading on the load cell minus the weight of the bottle at time 0, the weight of the water at time 0 minus the weight of the bottle. We'll call that equation 1b. Move over here. We substitute equation 1b into 1. On the left-hand side, we have R, so that's R prime minus WH2O at time 0 minus weight of the bottle is equal to thrust minus weight of the water minus weight of the bottle. We'll solve that for R prime, which is the readout. And the readout says thrust minus WH2O, that's the actual weight of the water, minus weight of the bottle, plus the weight of the bottle at time 0, plus the weight of the bottle. Well, the weight of the bottle cancels out. So what we're left with on our readout, this is what the readout says. It's the thrust minus the weight of the water plus the weight of the water at time 0. And I wrote that again just to remind you. This is the readout on the load cell. So what we're seeing on the load cell is not the actual thrust. It's the thrust minus the weight of the water plus the weight of the water at time 0. Okay, so this is our experimental portion of the project. Now we'll move over to our theoretical portion. We're going to calculate the theoretical thrust. Okay, from the linear momentum equation, we have this equation here. We have the sum of the forces. We have surface forces and body forces. We have the rate of change of momentum inside our control volume. And we're going to say that it's steady flow, or we're going to say that it's not changing very much compared to all our other terms. And this is approximately equal to 0. Plus this term here, well, if we integrate that, that ends up being our momentum flux. And so in the y direction, we have our surface forces, P atmospheric times A, minus P atmospheric times A, because we're saying the pressure, atmospheric pressure, does not change very much over the height of this bottle, minus R, minus the weight of the water, minus the weight of the bottle, is equal to minus rho V exit squared A exit. All right, so we'll solve for R. R equals minus weight of the water minus weight of the bottle plus rho V exit squared times the area of the exit. And we said R, we already derived this back in equation 1. R is equal to R prime minus weight of the bottle at time 0. I'm sorry, weight of the water at time 0 minus the weight of the bottle. So we plug that into this equation. We get this equation. Solve this for R prime. And then I'm going to take this equation here, we'll call this equation 3, and I'm going to substitute the results from equation 2 into this equation, and we get thrust minus the weight of the water plus the weight of the water at time 0 equals weight of the water at time 0 minus WH2O plus rho V exit squared A exit. Okay, so then we get that the thrust is equal to rho V exit squared AE, and A exit, so we'll call that equation 4. Then from equation 3, we also have the thrust is equal to the reading on the load cell minus the weight of the bottle, or the H2O at time 0, plus the weight of the H2O, and we'll call that equation 5. Now, in order to get the thrust, we need the exit velocity. So we'll start working on that now. To get the exit velocity, first we're going to use the Bernoulli equation. We're going to let subscript 1 represent the conditions at the top surface of the water, and E will represent the exit conditions. So if we write the Bernoulli equation, we have P1 plus 1/2 rho V1 squared plus rho GH equals P exit plus 1/2 rho V exit squared. From the continuity equation, we have that V1A1 equals V exit A exit. So we can solve for V1, and we get V exit, it's equal to V exit A exit over A1. So we'll plug that into our Bernoulli equation, and we get this expression right here. All right, so all I've done is I've rearranged until finally I get an equation here for V exit, and we have this, and then we have the areas here, so I rewrote it in terms of the diameter, because that's actually what we know. The exit velocity is the square root of 2 over rho times P1, which is the pressure in the bottle, minus P exit, which is atmospheric pressure, plus rho G times the height in the bottle, divided by 1 minus dE over d1 raised to the 4th power. That's our exit velocity. So you can see that to get our exit velocity, we're going to have to know the height of the water in the bottle from this term right here. And we don't know that yet, so we're going to have to derive an expression for that. Now the height is changing. What we'll do is we know the initial height because we measure that, and we're going to work in time steps of about 1,000th of a second, and we're just going to subtract, we're going to get an expression for dH, and each time step we'll subtract off that, and that'll be our new h. So over here I've said we need h to find V exit. All right, so we'll start here with our continuity equation. 0 equals dm dt, the change of mass with respect to time inside our control volume, plus m dot equals dm dt. Well, the mass flow rate is rho of the water, density of the water, times the velocity at the exit times the area of the exit. The mass inside the bottle is the mass of the water plus the mass of the bottle plus the mass of the air. So we take the derivative to get dm dt, and we have d mass of the H2O with respect to time plus d mass of the bottle with respect to time, derivative, and then the d mass of the air with respect to time. Okay, well, the only one that's not zero here, the bottle is not changing its mass, and the air is trapped inside the bottle, so its mass is not changing. The only mass that's changing is the mass of the water. Well, the mass of the water is equal to the density of the water times the volume of the water. The volume of the water is equal to, well, we'll write it like this, density of the water times area times little h, which is the height of the water. That does not include the nozzle. And then we have the volume of the nozzle times the density of the water. If we take the derivative of that with respect to time, d mass dt, the only term that we have to worry about is the water term. That's equal to rho of the water times the area, dH dt, plus rho d volume of the water dt. Well, the volume, volume of the nozzle, that's not changing. So that term goes to 0. And so we plug that in, and we get rho a dH dt, which is right here, has to equal minus rho of the water, B exit, A exit. Okay, we'll solve for dH dt, and we get minus VE AE over A, which is the area at the, in the bottle. We plug in our expression for V exit, and we get this term. I'm going to bring in A exit over A inside the square root, and we get this, an expression for dH dt. And we'll take that to the next step. T is given by this expression here. We have 2 over the density of water times the pressure in the bottle, P1, minus P exit, which is atmospheric, plus the density of water times rho, GH, divided by square of the area ratio minus 1. All right, we need the pressure in the bottle. That's P1. We're going to calculate that from the pressure of the air in the bottle. That's the pressure at the top of the surface of the water. Okay? From our isentropic relationships, we have that P1, this is the pressure in the bottle, divided by the initial pressure. That's equal to the ratio of the density divided by the density at the initial condition raised to the gamma power. Well, density is just mass over volume. Okay, so we have the mass of the air doesn't change. So we have mass over volume in the upper surface divided by mass over the initial volume, all raised to the gamma power. The masses cancel out. We're left with the initial volume divided by the volume. And that's equal to the ratio of the cross-sectional area times h minus the initial height of the water divided by the cross-sectional area times big H, the initial height, minus the current height. Well, the A's cancel out, and we're left with the pressure in the bottle of the air is equal to the initial pressure times big H minus H0 minus divided by H minus the current height raised to the gamma power. So we'll plug that into our expression for dH dt, and we get this expression here. Need to put a bracket right there. Okay, so I just plugged in our expression for P1 right here. So now it's written in terms of the initial pressure and the initial height and the current height. Now we need to integrate this expression to find out how the height changes during time. So what we're going to do is we're going to assume very small time intervals, and we'll assume that everything stays constant during that time interval. And a convenient time interval to use is 0.001 seconds, because that's how often data is read out to the spreadsheet. So when I integrate, if everything's constant, it integrates out nicely. We have this expression times delta t, which will be our 0.001 seconds, and that gives us how the height changed during that 0.001 seconds. So we come over here, we know the initial height. We're going to let delta t equal 0.001 seconds. We're going to plug that into our equation 7 that we just wrote up on the board. And this will allow us to calculate a new height at that time. So the new height will be the old height minus delta H. This is the height of the water at 0.001 seconds. We can now calculate a new exit velocity with the new height and a new delta, and we also need to calculate a new delta H for the next one. And we're going to just continue at 0.001 time second intervals. Okay, the new exit velocity is given by this expression. It's written in terms of the initial pressure, or no, the current pressure. But we're going to use our isentropic relationship, and we'll plug that in, and that's, we can now write the initial, or we can write the pressure in terms of the initial pressure and the height. And we know what the height is. Okay? We're going to take this expression for velocity, and we'll plug it into equation 4 for thrust. And that's going to give us our thrust at a particular instant. The thrust, you may recall, was given by, it's the momentum flux. It's density times the exit velocity squared times the area of the exit. Okay, so I wrote it down here. Density times area of the exit. The exit velocity squared is given by this expression right here. So it's in terms of H. It's the only thing that we don't know, or we have to calculate. So we have to calculate our H. H, again, is obtained using equation 7. And remember, the current H is equal to the old H minus delta H. One way to determine the performance of the rocket is to calculate the total impulse of the rocket. Okay, now you might remember from dynamics that force dt is equal to the derivative of mass times the velocity. If we integrate that, we get the impulse. So I is equal to the integral of f dt over our time interval. If we integrate dmv, we get mv2 minus mv1. Now the mass of the rocket has changed, so m2 is not the same as m1. F and v are both in the y direction, so we can drop the vector notation. So we take our integration here. We have f dt equals mv2 minus mv1. m2 will always be the same. That's the final mass. The final mass will just be the mass of the bottle. All the water has gone out. So it will be the same in all cases. M1 is going to depend on how much water is initially in the bottle. So it depends on how high you fill it up, M1. Okay? In order to get the impulse, instead of integrating, we're going to use discrete time steps, and we'll assume that the force is constant during these time steps. And we already learned how to calculate the force, which is our thrust. And then we can say that the total impulse, we'll call it I, will just be the sum of all the forces times the little delta t's, where the delta t's are our time interval, 0.001 seconds. And then once we know the total impulse, then we can use that to either maximize our V2 or whatever it is we want to maximize. Probably in this case, we want to maximize the final velocity. Okay, so that wraps up our the lecture portion of the pre-lab, and now we'll go into the lab demonstration.
Hi, I'm Kyle, and I'm going to introduce you to the Hydro Rocket test cell. This here is the control panel. You'll see the readouts for pressure, valves for air, water, vent, and your power switches. This is the test cell itself. Inside here, you'll load it up with water and then pressurized air. And when the plug comes out, so will the water very quickly. Before you begin with the hardware side, we'll need to start up this Rocket Lab experiment. It's a shortcut on your desktop called Rocket Lab, and inside of it you'll see several pages with step-by-step instructions. The first instruction here is to zero the load cell. This is so that we get an accurate force pressure. To do that, you begin by pressing the record button in the lower left, and you want to adjust this dial until the force reads out at 0. Make sure you do this before installing the plug or putting any water and air in there. Once you're at 0, you can press stop, And now we're going to start by filling the rocket cell with water. You'll probably find the plug inside the water tank. It's very rarely right there. And make sure that there's an O-ring on there and that it's a nice tight fit. You'll also see a hole through the plug where the retaining pin will keep that in there. You want to line it up with the two holes on either side of here so that you can get the pin in. And it takes quite a bit of force to work it in there. If you get the plug wet, if it isn't already, it'll make it a little bit easier. Once you have it in there, you want to insert the retaining rod. Well, make sure that it doesn't blow out until you're ready for it. So we can close this and power on the equipment. The main power switch here and the water pump switch here will start the water flowing. Of course, there's this water valve that you need to open and also an air vent to keep the pressure from building up as the water gets pumped. And if the water doesn't start flowing right away, cycle it off and then on. It'll help get it started again. Once you have the water filled to the desired level, you can see a metered height to the right. You can turn off the pump and close both these water valves and vent valves. Now, step 3 is to pressurize the rocket. If TA doesn't already have the lines pressurized, you can ask them to turn on the air compressor in the back. We've already done that. And we're going to open this line here to allow air to flow, pressurized air to flow into this unit. And you'll see on this reading here how much pressure you have coming from the wall. And you want to adjust this dial so that it reads below 60, between 50 and 60. Once you have that at that level, you can pressurize your rocket with this dial here. And you do the same thing, turn it until you get the reading you want. And bring it up to 50. And you'll see it static wherever you stop the rocket. Okay, now that you have that set, we'll go on to page 2, where we can run the test and view the playback. You may have to press this red circle button here in order to see the camera again, and you just want to make sure that it's lined up with the exit area of the rocket propulsion. This button down here, delete last run, will clear out the data that was recorded when you were zeroing the force pressure. Now we hit record, and it starts recording force and pressure. And we're ready here, so we pull the retaining rod, and you'll see it flow out. At this point, you can close your pressure there and stop your recording. Once you have your video and data recorded, you can adjust the graph by dragging between the numbers and stretching the numbers out. It'll help you find the exact time that you pull the plug. Each one of these squares or triangles is a point at which the video has a frame. So you'll see that you may be taking data points a lot more frequently than you'll actually see video show up here. And to sync your data with the video itself, you press this button here. It says sync video with data, and it allows you to control frame by frame of the video playout and of your data as well. So we'll go back to the very beginning here for both of these, and then slide through until you see where the point where the water blasted out. You want to do that for both the video, just to get a rough estimate of where it is, and then you go frame by frame to see where it is. So hopefully you can see this out where I've pulled the plug. I'm going backwards now. Alright, the plug hasn't blown yet, and we don't show a huge amount of force here, but we can go ahead a couple more video frames. Right there you see where the water and plug have been ejected. We'll just go one more frame, and it's a tough call. I'd say right here we start seeing some water expelling out, and that's right there where that is. Once it's synced up, you press this button again, and when you play back the video with the data points, they should now match. Alright, and you may notice that the audio is actually a little further ahead than the video itself. That's not a big deal. Mainly you're looking at the video and the data points. Now here in page 3, we can review and export the data. Basically we just want to copy and paste all of this and put it into an Excel spreadsheet, which we have in here in all programs, Microsoft Office Excel. And it'd be helpful if you have a USB thumb drive with you, or if you want to upload it to Dropbox or something like that, or email it yourself. That'd be fine. Just make sure you've received it, or that it has been uploaded before you leave, so you don't have to come back in and get that data.